Okay, so who remembers what we were discussing? Anyone remembers what we were discussing last when we met?
So square roots of some numbers.
Square roots of some numbers. Yes. Um, and we were looking at that because we were trying to understand equations and how they look in on a graph, plots of different equations, correct?
Yes, sir.
So what is the equation of a circle?
X square plus y square is equals to r square.
Yeah. So if the radius is 1 and if it is centered at the origin, then it is x squared plus y squared is equal to 1. Okay. And instead of x squared plus y squared equal to 1, if I say x squared plus 2y squared is equal to 1, then what shape will it be? Or x squared plus 4y squared equal to 1, then what shape will it be? Does anyone remember?
Sir, is it 2y whole square or 2y square, sir?
Yeah, 4y squared. So that is same as 2y whole squared. Then do you remember what happened to the circle?
Sir, elliptical.
Elliptical, exactly. And it'll get ellipse of which will be shrunk in one of the dimensions, along one of the axes. Which axis will it get shrunk?
What, sir?
It'll be same as a circle, but you have shrunk the circle. You have compressed it. Compressed it in which direction? X direction or Y direction?
Sir, towards x axis.
Towards X axis. So along the Y axis, you are shrinking it. So if this is a circle, then you're going to compress it like this and make it half the size. So here I can just show it here. So so this is the circle x squared plus y squared is equal to 1. And here is x squared plus 4y squared is equal to 1. And x squared plus 4y squared is the brownish plot, the brown or purple plot. And you see the purple plot is same as a circle, but it is shrunk by half. Okay. So like this, we can play with many equations. Like I can take any equation in x and y, and I will get some shape. I'll get some plot here. So for example, let's try some random thing. Let's try x squared uh, minus y squared is equal to 1. Do you see x squared minus y squared equal to 1? So let me remove the both of the other ones. Okay, so it's plotting all points so that x squared minus y squared is equal to 1. Okay, see how it looks? See how the plot of x squared minus y squared is equal to 1? You get this kind of shape. Okay, let's try something like x squared minus y squared minus xy is equal to 1. Okay, see this? How it looks? So I can put any equation and it will find me those xy's for which this is equal to, and I get different shapes. I can just put plot of x times y is equal to 1. Okay, and now let's see how it. Can someone think? Should I just plot it first, or should I? Do you want to guess how x times y equal to 1 will look, or should I just plot it right away? Does someone want to take a guess of how it will look? X times y is equal to 1. How will x times y equal to 1 look? Maybe think for a minute or so, couple of minutes. See how it will look. Think how it will look, and then maybe you can tell. And then we can try plotting it and seeing how it looks. X times y is equal to 1 is same as y is equal to 1 over x. Correct? Because I can just say x times y is equal to 1, divide both sides by x, and I'll get y is equal to 1 over x. So what is the plot of y equal to 1 over x look like? When x is very small, what is y? When x is very small, y is big or small? Anyone? Anyone has any idea? If I'm plotting y equal to 1 over x, what happens to y when x is very small?
Sir, if x is smaller, the y becomes bigger.
Yeah. When x is tiny, y is very large. And when x is large, then what happens to y?
Y is small.
Y is
Small.
small.
Y is small. So when x is coming very close to 0, then what is y? What happens to y? When x is
Y
coming very,
going.
very close to 0. Yeah, y is going to tending to what? As you make very, very small, it becomes closer to infinity. Correct?
Yes, sir.
Right? Yeah. So this is when x is positive. So when x is
Sir.
positive, so this is the curve. Okay. So x is positive, then y will be very large here when x is close to 0. And when you take x to be very large, then y is close, becomes very small, very close to 0. So as you make x goes to infinity, the y becomes close to 0. What happens when x is negative? When x is negative, but it is very small negative, then what happens to y? If x is like minus 0.0001, then what is y?
Minus, sir.
Minus large minus. So as x is becoming closer and closer to 0, but from the negative side, then y becomes more, like, becomes larger and larger in the negative direction. So it becomes close to minus infinity. And when x is very large negative, then y gets close to 0. So let's plot and see. Okay, so let's plot and see how it looks. Yeah, see, does everyone see this? So when x is very large, then y becomes small. When x is close to 0, it becomes closer to uh, infinity. And when x is negative, and when it's close to 0, then it becomes negative infinity. When x is negative and very large negative, then it gets close to 0. Okay. Now, in fact, actually, this is turns out this shape is actually called as hyperbola. Okay. So this, you remember this, we had shown this x squared minus y squared is equal to 1. Remember this x squared minus y squared equal to 1. Now, turns out they are about this. They're actually the same shape. Um, Actually, instead of xy equal to 1, let me make it xy is equal to 2. Okay. Xy equal to 2. Um, x squared minus y squared. No, sorry, wait. Let me try xy is equal to half. I'm just scaling it down. I'm just shrinking it. By changing that 1.5 and this, I'm not changing it much. I'm just shrinking it, making it like a little bit this. X So actually these two are here it doesn't look the same, but actually they are the same shape except one is rotated by uh, one is rotated by 40 degrees, 45 degrees. So let me just draw them separately. So you look at this shape, xy equal to 1. So this looks like this. And now separately look at x squared minus y squared is equal to 1. In both these cases, you see there are these two arcs. In one case, the arc, these two curves, in one case, the arc was like pointing like this and like this, in this case, pointing this. Turns out they're the same shape, except that the other one is rotated by 45 degrees. So this shape is called as a hyperbola. Okay. So any degree 2 equation, any equation which involves like only up to square, so only up to x square or y square or xy or x, y, and constant. So anything of that form, any equation you write that is going to be one of these three shapes, one of these 3 or 4 shapes. That is either circle or ellipse, or what is this? This is called a hyperbola. And there's another one called parabola. So these are 3 or 4 shapes, but they cover every equation of this form. So it's very interesting that you can take any equation of a certain degree. Here I'm taking degree 2 equations because there are highest power is 2. Do you all know what is degree of an equation?
Yes, sir.
Do people know what
The
is
highest power.
yeah, highest power? Yes. So What is the degree of a quadratic equation?
2,
Sir,
sir.
2.
2, sir.
Yeah.
2, sir.
So quadratic, when normally when we say equations, we only have one variable. We only have equations in x. Correct? Here we are talking about equations in two variables, x and y. Okay, but again, you can talk about quadratic equations in x and y. You can talk about cubic equations in x, y. Cubic means degree 3. So here we are talking about equations in two variables. When you take equation in two variables, then you start getting shapes. When you draw them on a plane, when you draw them in a graph paper, you start getting shapes. And it turns out that all equations of degree 2, you can, depending on you know, depending on what category it belongs to, it has only these 3 or 4 shapes, which is circles, ellipses, hyperbolas, and parabolas. Okay, how many people know what is how many people know what is ellipse? How many people know what is ellipse? How does ellipse look? How does ellipse look? Anyone? How does an ellipse look, Farah?
It was similar to like elliptical paths.
Yeah, but if, let's say, if I were to ask you, like, tell me some kind of definition or some kind of when would you call something an ellipse? Ellipse. So ellipse is nothing but a stretched circle. If you just take a circle and stretch it in any direction, that means you scale it in some direction, then it becomes an ellipse. So all ellipses are just things stretched in that direction. And parabola is exactly what you get when you throw a ball. Okay, parabola is exactly what you get when you throw a ball, and it basically has the formula y is equal to x squared. And then hyperbola is exactly these kinds of things, which is x squared minus y squared is equal to 1 is a hyperbola. Things of this shape. And turns out that any degree equation will be one of these 3 shapes. Either parabola or ellipse or a hyperbola. So circle actually is a special case. It falls already into an ellipse. It's a special case of an ellipse. When you don't stretch, when the stretch factor is 1, that means you don't stretch a circle at all, then it is exactly a circle. So circle is a special case of an ellipse. Okay, does that make sense? So do people understand how you can take any equation in x and y, and you will get some for every equation you can just plot it on the graph, and you will get some these nice looking curves, nice looking shapes on the thing. Is that clear? Is that clear to everyone?
Yes, sir.
Okay.
Yes, sir.
Does anyone have any questions about this? Anyone has any questions? Okay. Have you seen ever, like, what happens when you put a degree 3 equation? Like if I put x cubed here, then what happens? I think we tried this fourth power, right? Did we try this x to the power 4 plus y to the power 4 is equal to 1? And we saw that it was what? Does anyone remember what happens if we do this? X to the power 4 plus y to the power 4 equal to 1. Do you remember? You start getting closer to a square, right? The higher the power you make, you start getting more and more closer to the square. So x to the power 8 plus y to the power 8 equal to 1. Then I'll get even more close to a square. See this? So it's very interesting how you can get different shapes by just changing the equation here. So this shows the connection between geometry and algebra, right? Because I'm getting shapes which are geometric figures, and I'm doing that by using algebraic equations. Okay? Clear to everyone?
Yes, sir.
Does anyone have any questions on this thing? Or anything to discuss? Anyone wants to discuss anything? Okay. So um so far, so let me share this tab instead. Okay.
Sir, does we have the equation for square, sir?
Equation for an exact square.
Yes, sir.
Exact square. So you can't make it a polynomial equation. Like you have to take the power to very large value. The more larger the value you can make, the closer you will get to the square. So if you make x to the power 10 plus y to the power 10 equal to 1, okay, then you will see it's becoming even more close to a square. See this? But you have to make this power, if you make this power 100, then it'll become even more close. 1000 will become even more close. But to get exact square, you have to make it like infinity, a very large thing. But there's another way of writing a square, which is you say, like if I say x less than 1 and y less than 1. So I'm trying to do inside of a square, okay? So x less than 1 and y less than 1. So this is not exactly a polynomial equation, okay? But this is putting all points such that both x is less than 1 and y is less than 1. But I think so. Then actually it should have drawn. I don't see why it is doing. If you say x less than 1 and y less than 1, it should show negative, all negative things also. So so I don't know why it is showing. Okay, so yeah, so actually it is, yeah, so it is showing. So this is not exactly a square. Okay, this is not exactly a square, because actually if you had in this uh, paper, in this graph, even like far negative points, then those also would be under this shaded area. So here you're shading everything which satisfies this condition. So rectangle, the inside of a square is exactly those such that x is between 1 and minus 1 and y is between 1 and minus 1. So if I put x is less than 1 and y is less than 1 and x is greater than minus 1 and y is greater than minus 1, okay, now you'll get exactly a square. You see this? So this is actually not just a curve, this is actually the inside of that curve. So this is exactly a square, but this becomes an and of many conditions, many inequalities. So okay, let me remove this for a moment and just say plot. So x squared plus y squared. If I say x squared plus y squared less than 1, okay, tell me what will I get if I show x squared plus y squared less than 1? Which points will get shaded? So x squared plus y squared equal to 1, I was getting exactly points on the circle. But if I say x squared plus y squared less than 1, what all points will get shown? Will it still be only point? Will it still be points on the circle?
No, sir.
Which points will it be? Which point satisfies the condition that x squared plus y squared is less than 1? So it will be the points inside the circle. See this? It's gray. It's showing the points inside the circle. Why? Because any point inside the circle will exactly satisfy x squared plus y squared less than 1. Anything point outside the circle will exactly satisfy x squared plus y squared more than 1. And any point on the circle will satisfy x squared plus y squared is exactly equal to 1. So the moment I put an inequality, I start getting things inside a shape, the full inside the shape, not just on the boundary. So similarly, if I put x to the power 10 plus y to the power 10 is less than 1, then I get this almost rectangle, right? I get this almost rectangle. So inside, I get the inside of the almost rectangle. But this is not an exact rectangle. The exact rectangle would actually be like this. So I need to put an and of many conditions. So I need to say that plot x is less than 1 and x is more than -1, and y is less than 1, and y is more than -1. If I put all these conditions, okay, then I get exactly a square. Why? Because think about this. Think about if I say that x has to be between 1 and -1, and y has to be less than between 1 and -1, then that will exactly define a square here. So this is how you can exactly get a square, by doing an AND of many conditions. Okay, does that make sense? Any questions? Any questions about this? How to get a square? And why you get a square by putting these 4 conditions? Any question? Is it clear why you get a square by using these AND of these 4 inequalities? Right? You understand that? Right? Understand, right? Why when you say x has to be between 1 and -1, and y has to be between 1 and -1, then you get exactly the points inside the square. So by putting these 4 conditions, that is x is less than 1, and x is more than -1, and y is less than 1, and y is more than -1, you get exactly the inside of a square. Okay, let's move on to share this tab. Okay. So far we saw x squared, something like x squared plus y squared is equal to 1. We plotted this, right? And we get a circle. Now let's go to this equation. X squared plus y squared plus z squared is equal to 1. Z squared is equal to 1. So this is an equation in 3 variables. It has x, y, and z. Okay. Now, tell me, how would you plot this kind of an equation? How can you think about how you can get a plot of this kind of an equation? When you have 3 variables, what will you do? So remember what we did for when we were x squared plus y squared equal to 1, x squared plus y squared equal to 1. What did we do? We took an xy plane and we started putting points, drawing points wherever x squared plus y squared was equal to 1. And those points formed a circle. So that is how we converted an equation in 2 variables into a shape on a plane. Correct? Now if I have equation in 3 variables, like this equation, x squared plus y squared plus z squared is equal to 1, how will I convert this into a shape or a figure or something like that? So how do I draw this? How do I plot this? What is the meaning of drawing this equation, of plotting this equation? So we're trying to see the connection between algebra and geometry. Okay. X squared plus y squared equal to 1 is an algebraic equation. But we can convert it into a geometric shape by plotting it on a 2D plane. And the shape that we get is a circle. But for this equation in 3 variables, what should I do to be able to make it into a shape? Anyone has any idea? No? No one wants to take a try or shot? Suggest something? How would this correspond to some shape? How would you try to get a plot out of this? Can you draw it on a 2D plane? Can you draw it on an XY plane?
So maybe by drawing another line which is passing through the origin.
Yeah, that's right. What kind of line will you pass through the origin? What kind of another line?
So the line which satisfies the equation y is equal to mx, a straight line.
Y equal to mx. So are you saying something like this? So wait, let me just make sure I understand what you're saying. So are you saying you
Y
take
equal to
the
mx means 0.
sorry, repeat that once more. So this is xy, okay? So let's say this is the x-axis, the y-axis. So another line means what will you do? How will you do? Y equal to mx is just going to be a line which is something like this, right? Y equal to mx is just another line passing the origin. So are you saying you'll take this kind of line, these three lines? So this is the x.
Yes, sir.
This is the x line,
Yes,
y line. This is the y coordinate line. Okay, and then how will you plot this x squared plus y squared plus z squared is equal to 1 in this kind of a thing? Remember, I have three variables here, right? X, y, z. So instead of plotting an equation, let's just plot points. So, for example, on a 2D plane, on an xy thing, I can say, so like on 2D, I can say plot the point x equal to 1, y equal to 2. So I can draw this, right? I'll show it that is here x equal to 1, y equal to 1. I'll draw it somewhere here. But when I have three variables, let's say I want to plot x equal to 1, y equal to 2, and let's say z is equal to 3. How will I plot this single point? Or let's just say x equal to 1, y equal to 1, z is equal to 1. Something like this. Okay. So if I want to plot x equal to 1, y equal to 1, I can easily plot that on a 2D plane, two-dimensional plane, correct? With x and y axis. But if I want to plot this one point which has three coordinates, x, y, z, then what will I do? Can I draw it on that thing that you were suggesting? That is, you take x and y and you take one thing passing through the origin. In this, can I show x equal to 1, y equal to 1, z is equal to 1? So I should be able to take any three coordinate values, x equal to 5, y equal to 7, z is equal to 13, and I should be able to draw a point. How will I be able to set up some coordinate system to do that? But your idea was correct. Like you take another line passing through the origin. That idea is correct. But think a little bit more along that. Can you draw x equal to 1, y equal to 1, z is equal to 1? So who suggested that? Maybe you can unmute and I can try to help you. Who suggested passing through the origin? One of you suggested that. Can you raise your hand? Okay, Mahalakshmi. Okay, so just unmute yourself. So if you make it like a line passing through the origin, like this, okay. So is that the z line? Are you thinking of that as the z axis, Mahalakshmi?
Yes, sir.
Okay. Now, if you make that as a z axis, then if it is in the same xy plane, now when I choose a value of x and when I choose a value of y, then is the z value fixed or not fixed? Like in an xy plane, I can freely choose any value of x and any value of y. Right? If I just have x coordinate, y coordinate, then remember that I can take 1, 1 is here, 1, 2 is here, 2, 1 is here. I can take any two values of x and y, and I'll get a point for that. And now I want to set up three coordinate system, x, y, z, and I want to do it in a way so that I can take any three values of x, y, z, and I should be able to get a point there. So will it work if I do it in the way you're saying? That is, I just pass a line, 45-degree line passing through the origin. Will it work? Can it ever work on a two-dimensional plane? Can I set up this x, y, z coordinate system in a two-dimensional plane? What if I go to 3 dimensions? What if I try to plot it in 3 dimensions? Can I do it that way? How will I get 3-dimensional coordinate system? So I have x, I have y. The third one, what will I do? What is the third z axis? How will I do? How will I set it up to get 3-dimensional coordinate system?
sir. Cross
Repeat that.
passing to origin.
Passing the origin and pointing which way?
Cross, sir.
Cross. Yeah. Perpendicular to the xy plane. Correct?
Yes, sir.
Perpendicular xy plane. Yeah, exactly. So like this. So I don't know if you can see this, but like this. Yeah, do you see this? It's like this. X, Y, and Z like this inside. Or I can also show it on a figure here, picture here. So, yeah. Do you see, for example, here? Yeah, like this. Okay, so this is X, this is Y, and the Z is coming out like this. Okay, like out here, this X, Y, Z, three-dimensional coordinate system. So now when you take a point like 1, 1, 1, it'll be a point in this three-dimensional space. So in this three-dimensional space system, you can take any triple, you can take any, in an XY plane, you just take two numbers, right? You get X equal to 1, Y equal to 1, and you get a point, or X equal to 1, Y equal to 2, and you get a point. So any pair of numbers, and you can draw that on a two-dimensional, on a 2D coordinate system. In a 3D coordinate system, you can take any three numbers and you can just draw a point in a 3D space. So it'll become like a 3D space. Does that make sense? Mahalakshmi, does that make sense? Is that clear?
Yes, sir.
Yeah. So do you understand why I need to make the Z perpendicular to the XY? If I make it perpendicular, then for every XY and I can take any value of Z. Because if I take X equal to 1, Y equal to 1, I should be able to take any Z value. I should be able to take Z equal to 1, Z equal to 2, Z equal to 3. And I can do that only if Z is perpendicular to X and Y. And the moment you make Z perpendicular to XY, it becomes a three-dimensional space. Okay, so in three-dimensional space, when I set up this X coordinate, Y coordinate, and Z coordinate like this, perpendicular to it, then suddenly I start getting now, instead of two coordinates for every point, I can start getting three coordinates for every point. Every point can be determined by three numbers. So you can just call the first number X coordinate, second number Y coordinate, and third number Z coordinate. And now, once you have an XYZ coordinate system, XYZ coordinate system, now you can start plotting equations in three variables. So you can now start plotting this kind of equation. X squared plus Y squared plus Z squared equal to 1. So do you understand how you need to go to three-dimensional coordinate system to plot an equation in three variables? Does that make sense? Does that make sense to people?
Yes, sir.
Now, can anyone try to guess or think, if I plot this equation in a three-dimensional coordinate system, that means, now remember, in a three-dimensional coordinate system, for any three numbers, I can put a point. And every point can be specified by some three numbers. Now, if I take all those points which satisfy this equation, which satisfy X squared plus Y squared plus Z squared is equal to 1, then what shape will I get?
Sphere,
So,
sir.
yes, that's correct. So you get a sphere. Can you tell me why you get a sphere?
Sir, in 2 dimension, x to the power of 2 plus y to the power of 2 equal to 1 is circle, sir. When 3 dimension, it is sphere, sir.
But do you know for sure, or are you guessing?
Guessing, sir.
Okay. So your guess is correct. It is actually exactly a sphere. Now, I don't know if we can plot three-dimensional things in this wolframalpha.com, but let's try. I think it might work. It might show it exactly. X squared plus Y squared plus Z squared is equal to 1. Okay. See what it draws. Okay. See, look at this. Look at what it drew. Right? So it is actually can draw. This tool, this particular web page, can actually draw three-dimensional coordinate system. So it is showing you, right? It's showing you, see, the y-axis is here. The x-axis is here, the z-axis is here, and the y-axis is here. Okay, so this is x-axis, z-axis, and y-axis. And you can see it's actually drawing a sphere. Do people see this?
Yes, sir.
Right. So Is this interesting that you can actually take some equation in 3 variables, you can draw it in a 3-dimensional coordinate system, and you can get nice shapes like spheres? Is this interesting?
Yes, sir.
Yes, sir.
Yeah. So this is how you can get really, like, you can take any equation and you can draw it in some coordinate system and you can get beautiful shapes. What if you had 4 variables? Then what would you do? What if you have x, y, z, and u? And let's say you want to plot x squared plus y squared plus z squared plus u squared is equal to 1. Then what would you do? Is there a way to plot
Pentagon.
it? Pentagon. So you have 4 variables. Okay. So remember, to have, when you have 3 variables, when you have 2 variables, you want it on a 2-dimensional coordinate system, which is x-axis and y-axis on a plane. Okay. Then when you had x, y, and z, then you had to go to a 3-dimensional coordinate system. You had to go to x, y, and the z axis, which is coming out of the plane, xy plane. And then you got a sphere. When you put x squared plus y squared plus z squared is equal to 1, you got a sphere. Now, if you have 4 variables, x, y, z, u, what dimensional coordinate system do you need? Is three-dimensional coordinate system is going to be enough? Is it going to be enough? 3-dimensional coordinate system?
Sir,
Yes,
4D
sir.
dimension.
4
What
dimensions.
dimensional? 4 dimensional.
4 dimensions.
Exactly. You need a 4-dimensional coordinate system. Correct?
Yes, sir.
Now,
Yes, sir. Yes, sir.
now this space that space around us is what dimensional? What is the dimensionality of a space around us?
3-dimensional.
3-dimensional. Correct. So can we ever draw a 4-dimensional, or like, can we ever realize a 4-dimensional coordinate system in a 3-dimensional space?
No, sir.
No, that's right. So can we even imagine a 4-dimensional space in our head, in our mind? Is it possible to imagine a 4-dimensional coordinate system? Is it possible to imagine a 3-dimensional coordinate system in our mind? 3-dimensional is possible in
Yes,
our
sir.
mind?
Yes, sir.
Yes,
Yes.
sir.
Yeah. Correct. It'll just be like this, something like this. We can even actually draw it using sticks. In fact, this whole space is 3-dimensional. Is it possible to imagine a 4-dimensional coordinate system?
No, sir.
No, sir.
No, sir.
No.
No, sir.
Right. Our mind and our eyes are all built for 3-dimensional world, because this world is 3-dimensional. Okay. But can we algebraically write down, like we went from circle to sphere? Okay. Can we imagine a 4-dimensional sphere? So we can imagine circle, we can draw circle, we can imagine sphere, we can even make things which are sphere shaped, 3-dimensional sphere. What about 4-dimensional sphere? Can we imagine it?
No, sir.
No, we cannot imagine it. Our mind and our eyes are all can only imagine and look at 3-dimensional.
3-dimensional.
Algebraic equation for a 4-dimensional sphere. Can we write it down? Can we write down the equation for a 4-dimensional sphere?
Yes, sir.
What is the equation? How will you write down the equation for a 4-dimensional sphere? This is circle. Okay. This is equation of a sphere. It's called a 4-dimensional 4D hypersphere. Okay. And this way you can actually write down equations for any dimension, 5-dimensional hypersphere, 6-dimensional hypersphere. Okay. Let's look up in Wikipedia. Okay. Hypersphere in Wikipedia. N sphere. It's called an n-dimensional sphere. Okay. Can you read this? Can you see this, everyone?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. Okay. So it says that in mathematics, an n-dimensional hypersphere is a shape that you get in a n plus 1 dimensional space. So basically, the circle is like a the is like a line. It's a curved line, right? So it's like a 1D line in a two-dimensional space. The sphere is like a 2D surface, curved surface in a three-dimensional space. Okay. A fourth sphere is a hypersphere, which is like the surface of the fourth sphere will be three-dimensional, but actually be in four-dimensional space. Now we can't visualize all these things, but we can write down equations like this. So in geometry, we cannot visualize geometrically we cannot visualize a four-dimensional sphere, but algebraically we can write down these equations. So do you see the power of how algebra can help us represent, capture things which we cannot even imagine? So we can imagine circle and sphere, and we can write them by equations. Now, but a four-dimensional sphere, we cannot imagine it, but we can write all the equations. So these equations and algebraic ways of imagining things help us talk about things which you cannot even imagine. Okay, does that make sense?
Yes, sir.
Yeah. Similarly, you can talk about square. So square is whatever is square is a two-dimensional object, correct?
Yes,
When
sir.
you
Yes,
go
sir.
to three dimensions, what does the square become?
Cube, sir.
What becomes
Cube, sir. Cube.
cube? Correct. What if we go to four dimensions?
Hypercube, sir.
Hypercube, exactly.
Hypercube,
Yeah, hypercube. Okay, let's look at this. Let's search for hypercube. See what comes up.
sir, hypercuboid.
Hypercube. Yeah. So if you take a square, the square in three dimensions.
Sir, hypercuboid is four dimensions, sir. Cuboid. Hypercuboid, sir.
I think cuboid is more general. Cuboid is like a parallelepiped. It's actually exactly hypercube. But actually, the hypercube refers to a cube or a square in any number of dimensions, like in n-dimensional hypercube. But if you take the four-dimensional hypercube, so this is the four-dimensional hypercube. Oh wait, let me share this. Sorry, I forgot to share this. Okay, so you leave this hypercube. So there is the three-dimensional cube, which is the normal cube. A two-dimensional cube is exactly a square, and a four-dimensional cube is actually called as it has a special name. When you go to four-dimensional hypercube, it's exactly called a tesseract. It has a famous name called tesseract. Now you cannot imagine these things, but you can write down equations for these. So this is how algebra helps us in talking about things and analyzing things which we cannot even imagine. Okay.
Sir, hypercuboid, sir.
Actually, it's hypercube. Cuboid is slightly different. Cuboid is, let's see, what is cuboid? Cuboid is, I think, like cuboid is like rectangle. But if we are going to equal sides, all sides being equal, then it is exactly square, hypercube, and four-dimensional hypercube is a tesseract. Now let's go back to this another plot in two dimensions. Let's come back to two dimensions. Okay, let me share this one again. Now, do you remember the sine? Do you remember that sine of theta? There's a function called sine of theta. Do you remember sine theta? Who remembers the definition of sine theta? Anyone remember the
Sum of
definition of sine theta?
hypotenuse and opposite sides.
Just repeat once more.
Sir, the sum of hypotenuse and opposite side in a triangle.
Sum of the hypotenuse. What do you say? Sum of. Repeat once more. Sum of. Is it sum of or is it ratio of? Which one is it? What is sin x? It is. So we have done this. So let me go back to that slide if we have it. Let's see.
So the ratio of opposite side to hypotenuse.
Exactly. It's the ratio of the opposite side to this. Exactly. It's not the sum. Okay. It's the ratio. So this was the slide which showed sine. Where was it? Yeah, this was sine, right? You take any right triangle, and this is theta, and it's the opposite side divided by this one. Okay. And now this theta is so in this right angle triangle, theta is some acute angle, right? Something between 0 and 90 degrees. But can I have sine of something more than 90 degrees or 90 degrees also? See, we can also define sine theta by looking at the circle. Okay. So when I want to take sine of a certain angle, can I say that it is the height of the point? So let me take a unit circle. Let me take a circle of radius 1. Okay. So what I do, I have a circle of radius 1. So I can take a circle of radius 1. I can rotate the x-axis by, I can take some units length along the x-axis, and I can rotate it by theta. And I can look at the height of that point. That height of that point is exactly the opposite, the side of the opposite thing, right? And that height, if the radius is 1, then that height is exactly sine theta. Why? Because the ratio of that height to 1 is exactly sine theta. So the height of a point is same as the y coordinate, right? The y coordinate is exactly the height. So the y coordinate of a point, so I just start from the a unit radius here, and I rotate it by theta, and I look at the y coordinate of that point. So now I can talk about sine of not just an acute angle, not of an angle less than 90, but can I also talk about angle which is more than 90? If I just call it as the height of the y-axis of that point after rotating by theta, then do you see how I can say what is sine theta, not just for when theta is less than 90, but also when theta is more than 90 degrees? Is it clear? Is it clear how I can talk about sine theta when theta is more than 90 degrees? So I just take this. So here it was this thing O to this point. Okay, this O point. I rotate it by theta. So here, for example, I've rotated by 45 degrees, and I just look at this height. The height is same as the y coordinate. And in case of, if this is a unit circle, then this height is 1 over root 2. And that's why sine of 45 degrees is exactly 1 over root 2. But I don't need to take sine of only angles which are less than 90. If the angle is more than 90, I just keep rotating it further, and then I take the y coordinate of that point. So by that definition, can someone tell me what is sine of, first tell me what is sine of 0 degrees? What is sine of 0 degrees? Okay, what is sine of 45 degrees? We did all these things, right? What is sine of 45 degrees? Anyone remember sine of 45 degrees?
So 1 by root 2.
Yes, correct. What is sine of 30 degrees?
1 by 2.
Yeah, 1 by 2. What is sine of 0 degrees?
0.
0, exactly. Because if I take an angle which is 0, then this height here, opposite side is 0. What is sine of 90 degrees?
1. So 1.
1.
1. Correct. Okay, because I'm taking all the way here. So I'm taking this, rotating it all the way here. Now the height has become 1. Okay, now tell me what is sine of 180 degrees? If I take this and I rotate it all
0.
the way to 180 degrees, how much is
The
it?
sine of
0.
180 degrees. 0, sir.
0, sir.
Yeah, correct. Okay. What about sine of 270 degrees? 3 times 90 degrees.
So minus 1.
Minus 1, correct.
Minus 1.
Why? Because I'm going to take this and I'm going to rotate it 90 degrees, another 90 degrees, another 90 degrees. So it's going to go down. So the y coordinate will become minus 1. Okay. What is sine of 360 degrees?
0, sir. 0, sir.
Yeah, exactly. So Sine of 0 is 0. Sine of 90 degrees is 1. Sine of 180 degrees is 0. Sine of 270 degrees is -1. Sine of 360 degrees is 0. And I can keep adding 90 degrees. 360 plus 90 is 450. Sine of 450 degrees is 1. Sine of 450 plus 90 is 540. 540 is 0. So it'll keep getting back to the same values. Okay. Okay. Now what is sine of 90 plus 45 degrees? 90 plus 45 is 135. What is sine of 135 degrees?
1 by root 2.
Yes, 1 by root 2. Is this clear to everyone or only some people are answering? Is it clear to everyone why sine of 0 is 0, the 90 is 1, 180 is 0, 270 is -1, 360 is 0, then 450 is 1, then 540 is 0, and then 630 is -1. Is that clear to everyone? Why it is like that? Why it is repeating again and again?
Yes, sir.
Everyone is clear? Anyone is not clear about this point? Everyone's clear?
No, sir.
Sure, everyone? Now, so if it's clear to everyone, now I can now plot a function, plot y equal to sine x, where the x-axis is the angle and y is the sine x. So I can plot something like this: y is equal to sine x. Correct? How will this look? Like this: y is equal to sine x. So x is the angle and y is the sine of that angle. Anyone wants to guess how this will look? How will y equal to sine x look? Anyone wants to guess? Or should I plot? So it's going to keep changing from 0 to 1 to minus to 0 to -1 like that. 0, then 1 by root 2, then 1, then 1 by root 2, then 0, then -1 by root 2, then -1, then -1 by root 2, then 0, like that. It's going to keep changing. As you keep increasing the angle, it's going to keep repeating back to these values. So it has a very interesting plot. Let's look at the plot. Okay. So here's the interesting plot. Let's plot. Okay. Do you see this? Okay. Look at this plot here. Do you see this?
Yes, sir.
Yeah. How is it looking? Do you understand why it is looking like this? So at 0, it is 0. Then slowly it increases to 1. Then slowly it decreases to 0. Then slowly it decreases even to -1. Then slowly it decreases again to 0. Then slowly it increases to 1. So it's like this. Like this, like this, like this, like this, like this. What does this look like? What does this look like? Here is some other ways. Here are some other plots that show this. Look at this one. See, this is like a sine. This is like a sine y equal to sine x plot. So tell me, what does this look like? What does it remind you of? This kind of thing. What is it? Is there something that comes to mind by looking at this? What would you call this? What shape would you call this? If you didn't know about sine x, what shape would you call this?
Wave, sir.
Wave. That's right. Where do we see waves? Where do we see waves like this?
That sound waves.
Sound.
Yeah, but sound waves we can't see, right? We can't see sound waves. Tell me some place where you see something like this.
Sea wave.
Water waves.
See, sir.
Water. Yes. Okay, let's look at some water waves. Okay, let's see. You see this image here? Okay, this is, so this is actually showing many, like if I throw a stone, then you see these ripples coming out. So those ripples are actually
Yes,
like
sir.
are exactly like a sine wave. So they are exactly like if you take a if you take a if you take a stone and you periodically like put in and out of the water, then you exactly get a sine wave. Okay. Or have you ever played with a carpet? If you take a carpet or a chatai or something like that, and you keep doing like this, then what shape
Yes,
will you
sir.
get? Yeah,
Yes,
then you
sir.
get exactly yours.
Yes, sir.
So that will exactly match this equation. So what you can actually, they can actually derive this. So let me try this sine wave in carpet. Let me see if I get that. Yeah, I need to figure out. There are lots of nice videos where they will show how you take a carpet and you do like this, and it'll exactly form a wave. And that wave exactly matches this equation y equal to sine x. So you can actually prove and derive using equations of motion and all those things that y equal to sine x. So the y equal to sine x thing is true for many phenomena in real life. So it's true for water waves, for sound waves, for carpet, like when you do this kind of thing. Even springs when they go up and down, like the way when you take a spring and when you make it bounce up and down, then as a function of time, the height as a function of time, when you plot it, it becomes exactly sine wave. So this was the sine x function, y equal to sine x function is very important function that we encounter in real life. Any questions? Any questions about this? Any questions? If not, we can close for today. If you have any final questions, we can feel free to ask. Okay, so is it clear how why this y equal to sine x has such like this kind of plot? Because it's as the angle changes, it goes from 0 to 1 and then back to 0 and -1 and again 0. It goes as you keep increasing the angle, keep repeating the same values. And this equation, that is up down up down up down equation, is exactly looks like a wave. And this wave is something that we see very often in real life. Okay. Okay, if there are no other questions, then let's close for today and we can pick up next time. Okay, thank you.